mathematical peculiarities of the UNIV SLinX, and a challenge to the low-dimensional topologists by UNIV. UNIVs are artistic manifestations of gems, which in turn is a class of four regular, four-edged, colored, finite bipartite graphs. In what follows, a 3D universe is a closed, orientable three-manifold. Every 3D universe is induced by a gem, hence by an UNIV. In fact, it's induced by infinite gems. Of these, one can distinguish the ones with a minimum number of vertices, naming this set the attractor of the 3D universe. By using lexicography, we can distinguish further a specific gem, naming it the canonical gem of the 3D manifold. This induces a one-to-one correspondence between 3D universes and a subset of gems. Also, there is an efficient heuristic procedure to produce the attractor from any of its gems. Every closed orientable 3D universe is also induced by a blink, which is simply a finite graph with a bipartition of its edges. This was, with another language, proved by the distinguished topologist Raymond Licorice in 1962. These two presentations of 3D universe are complementary. Gems are good to prove that the two 3D universes have the same shape. Blinks are good to prove that two 3D universes have not the same shapes. Therefore, it would be important to have a general efficient procedure to go from a blink to a gem, inducing the same 3D universe, and vice versa. From blink to gem, we have such a procedure. A linear algorithm given in the Annals of Mathematical Studies, 134, published by the Princeton University Press, authored by Louis Kaufman and UNIV. However, from gem to blink, the algorithm which constitutes Licorice's proof contained in his 1962 paper is highly exponential and so extremely inefficient. Along more than 2 decades, we have been trying to produce an efficient such algorithm. Last year, there was some progress, which we report briefly in what follows. From a gem, we have an efficient algorithm to produce a positive number named the deepness of the gem. As a consequence of a result proved in Ricardo Machado's thesis last year under our supervision, if a gem has deepness 1, then there exists a quadratic complexity algorithm to produce a blink inducing the same 3D universe as the gem. From a complete general catalog with around 76,000 gems inducing all small 3D universes, only about 4,000 have deepness greater than 1. Thus, currently you can display blinks associated to most small 3 gems. Another fact we prove is that given any 3D universe U, there exist gems of deepness 1 inducing it. Unfortunately, the gems which prove the theorem are born from blinks inducing U, and so do not help in our search. There are 4 nice properties of the UNIV SLinX here present, which we enumerate. First, SLinX is the first UNIV whose gem has deepness 2. Second, it is the only gem in the attractor of its 3D universe. 3. It can be presented by a gist or a string presentation, implying that all its 3 residues are isomorphic. 4. The gist is unique. Usually for K4 symmetric gems, there are many gists encoding various distinct K4 symmetries of such gems. Let X be the 3D universe induced by the UNIV SLinX. We propose the following challenge to the low-dimensional topology community. Find a blink, or what amounts to be the same, a framed link inducing X. Because of its rather peculiar behavior at this time of our acknowledgement of 3D universes, we have distinguished SLinX by constructing it in steel, obtaining a nice mathematical sculpture with a bounding box of 1300, 900, 900 millimeters. Note that SLinX is the smallest UNIV for which we do not know how to find its associated blink. This UNIV is the first one manufactured in polished steel.